Welcome back, my fellow colleagues. This is, first time doing this problem, by the way. This is 104, maximum depth of a binary tree. This one's not too bad, but the thing with this one is you shouldn't start writing code until you actually understand the solution. So you can actually write the solution, right? For many problems, I guess it's just a general rule. You can write the solution for most problems in just pseudocode, which is why whiteboarding / pseudocode is good, before you even write a single line of code, right? So if the series of logical propositions make sense, then you can just write the code for it, right? But irrelevant, that's the problem. Given the root of a binary, so we're going to solve the problem first, and then we're going to draw it. Given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is a number of nodes along the longest path from the root node down to the farthest leaf node. So basically what they're asking for in a way is kind of the reverse of the classic shortest path thing, right? So we just want the longest path, right, which is just going to be 327, right? But what it's kind of saying is that it wants the depth, right? So it's just the node, right, that are the farthest leaf node, right, from the root. So if we had one more node here, that would be 4, right? So 320. So right, left to get 20 down here. But you can see for this example here, the maximum depth of this tree is going to be 3, right? Because the root counts as one level, second level is the second, and the third is the third, so you have 3 levels, so the depth is 3, the maximum depth. You have some more here. They're saying, hey, if there's no root node, then obviously the depth is 0. If the root node is only 0, right, so if there's only one element, right, so if the tree is just one element, right, so imagine just a 3 here, then the depth is 1, right? So how do you solve this? So you can actually do this from a top-down approach, right? Because at the end of the day, the solution is built from maximizing, right, the depth of the left and right subtrees. If you're looking at this from top-down, right, we're starting at the root, so it's intuitive to look top-down, right? So how would you find the maximum depth, right? You would just keep taking the maximum depth provided by the left or the subtree, right? And you can actually run with this proposition, right? So we'll say, hey, start at the root node, and we'll take the maximum depth of the left node, and it's left subtree, and it's right subtree. So we'll go down the left subtree. We go to 9. Okay, that's 2, right? Well, we can't go any further, so it's 2, right? 2 on this left-hand side. And we go down the right-hand side, we'll see that we can go many ways, right? We still end up with 3, right? If you take the max of the depth of this node right here, which is 20, right? No matter if you take 3, 20, 15, or 3, 27, right? The maximum depth is 3. So the max of 3 or 3 is just 3, right? When I'm saying max, I'm talking about the max function, right? So it's going to return the maximum of 2 values provided, right? And so you can kind of take this naive approach and this naive top-down approach and kind of solve the whole tree this way. Right, and what you get is that the solutions will actually bubble up back to the top. Well, we'll find that the last question really is just the first question, right? So the first question we asked was, hey, which depth is larger, the maximum of the left of the root or the maximum of the right? I mean, which depth is larger of the left and right subtrees of the root, right? We'll take the max of that, right? And the max will give us the largest depth. But that question, which we start with, is also the last question, right? Because as we go down and solve these problems, the way the recursion works, we'll bubble up back to the top and we'll be able to answer our original question. What you end up with here, right, is the maximum depth of the left tree is 1, and the maximum depth of the right tree is 3. And then the final question you ask is, which is bigger, 1 or 3? 3, so the maximum depth is 3 here. So how do you solve this, right? So what we'll do, right, to start is we're going to write a function, right? They gave us a function here. And I guess you could solve it with that, but it's just more intuitive to not solve it with that. We'll call it self.count depth, and we'll just pass in the root. Okay, and then we'll write the function here. Count depth, we'll pass in that, and we'll just call it node, which is just a general node that we're going to pass in. And you can see that for self, we're passing in root, right? So let's handle the base case. I mean, not the base case, but the problem kind of cases, right? So let's just say, right, that they pass in a node, right, and there's nothing in it. They gave us a root node, right, and there's just nothing in the tree. There's just nothing there, right? So obviously, if node is none, right, and we should return 0 because there's no maximum depth. There's no maximum depth to be had, right? Because there's no elements in the tree, right? Otherwise, though, then we'll actually try and solve the problem. What we'll say, right? Remember, is that the problem just boils down to which tree is bigger in the root, the left subtree or the right subtree. And so let's do that here. We're just going to take the max of both of these trees, and what we'll find is that the problem is solved with this top-down approach. So we also have to add 1 here, right? And I'm going to finish writing this and I'll tell you why. So we're going to do 1 plus self.countDepth, right, node.left, and we're going to slide over 1 plus self. Let me give it some space. Self.countDepth node.right. So why are we doing this, right? Just like we said earlier, and if we run this, we'll see that this works. But why are we doing it this way, right? Well, we said that the first question we ask, right, which is really the only question we ever ask, is which of the subtrees for a given node has a deeper depth, right? Return that one. So we're passing in the root node, we're saying, hey, give me the max, passing in the root node, give me the max of the depth of the left subtree or the right subtree, right? We have to pass in 1 though, right? Because we said the node wasn't none, right? So if the node isn't none, right, it means that the node exists, right? If the node exists, then we want to kind of keep a running sum, right, of the depth we're at. So we're adding 1 because we're acknowledging, right, that node.left and node.right both have a parent, and that parent consists of a node. And if you have a node as a parent, it means you're part of a level, right? And so it's kind of this logical construction of propositions here. So we're saying, hey, imagine you're at 20, right? We're saying, we'll take the maximum of the left subtree and the right subtree, right? Well, 15 and 7 are both children of 20, right? And if we want to get the depth of 15 and 7, we're going to have to add the depth to where 20 was at, right? Because we went 3, 1 plus 1 is 2, plus 1 is 3, right? To get here, right? And that's important, right? And so we're going to work through the code now in Sketchpad. And what you're going to see is as we follow this through, this is the same, kind of the same problem we're working with here, but a little bit more of a more simpler version of it. So I'm going to make this an 8. And so our code is up here, right? We said if the node is none, return 0. Otherwise, return max of 1 plus count depth of the left subtree and 1 plus the count of the right subtree, right? So give me the maximum of these two subtrees. So let's follow that, right? So I have R here, right? R is going to be equal to root, which is going to be equal to 1 here, right? And so we're using R here, but you could write 1 if you wanted to. And then we're just going to follow this line by line. So let's follow it. So we're calling, in our original example, we're calling return self.countDepth root. So we're starting with the root, right? So R here is going to be the node on the right before the colon is always going to be the node calling the function, right? So we said, well, R is clearly not none, right? So we have to do return max of 1 plus self.countDepth node.left, or the max of this one or this one, right? And that's what we have here, right? So we have the max of 1, right, is 1 plus, and the max of 1 plus the right node, or the right subtree, right? And so the line I've put under here, right, means we don't have the value yet, right? But I've put 2 to signify what node that would be. So if we take a look at here, we'll see that R, which is 1 count, called the function, the recursive function, and we want the max of these two values, right? Well, we know that the first value is 1, and the second value is defined by self.countDepth node.left, right? So let's call that function, right? So we'll bring an arrow down here, and we said that we'd write the number before the colon as the number calling the function, or the node calling the function, right? And let's just run the code in our heads, right? So now we're calling it with 2. Is 2 none? 2 is not none, right? So we have to return the max of 1 plus self.countDepth node.left. So we just put a line here, right? Because we can't calculate that yet, right? So you want the max of the left subtree or the right subtree plus 1. So we'll put another line here, right? Because we didn't get a chance to calculate that yet, right? And so what are the left and right nodes of 2? Well, the left node of 2 is 8, and we'll write that under here just to make this more intuitive. And 2 has no right node, right? So we're just going to write X here for null or none, right? So we're going to have to keep going, right, with this in the recursive fashion with, left to right, right? So this function is going to get called now, right? So now we're calling it for 8. So remember we said the number before the colon was the node calling the function, or the node that we were maximizing its left and right subtrees for, right? So let's call it for 8. If node is none, well, 8 isn't none, so let's return the max of 1 plus blank, or 1 plus blank, right? And what's the left and right subtrees for 8? Well, they're both x, right? They're both none. They don't exist, right? And we said, hey, if they're none, right, return 0. So obviously we're going to call count depth here, right? But to save, I guess we're just going to do it anyway, but we're going to say, hey, x, which is none, right? What do? X is the one that we're calling, x is node, right? If node is none, well, we're going to return 0. Well, okay, if that's true, then we're going to return 0. So we're going to return 0 here. Well, we also have to do it for this x, right? So we're going to do it again. We're going to go, oh, wait, x is none, return 0. So you can see how the first question we ask is the question we're going to ask for every single node, right? And now we can start bubbling this up to the top. So we said this first part here was going to be the result of this, right? So what's the result? What's the max of 1 plus 0 or 1 plus 0? They're both 1, right? So it doesn't really matter. They're both 1, right? So now we know that at 2, we have at least a depth of 2, right? So now you have to evaluate the right-hand side of 2, right? Well, we said 2, the right subtree of 2 is none or null, right? So it's going to return 0. And we can kind of just walk through that here, but we said it before. If we call count depth with a null or a none node, we're going to return 0, as we can see up here. So we can just keep using this one call we did down here, and we'll always see that whenever we call it with none, it's going to be 0. So which is bigger, 2 or 1? 1 plus 1 or 1 plus 0? Well, 2 is, right? So you return 2, and that shoots back up here. So now we were able to solve with a top-down approach, right, the first half of our original question. Now we know that the left subtree for the root node is 3, the depth is 3, right? But we said do the right-hand side. So we said that we'd write the number, or the node that's supposed to be called with the function under the line, right? And we'll do that one over here. So now we're calling it with node 3. Node 3 isn't none, so let's return the max of 1 plus blank of 1 plus blank, right? Well, what are the left and right nodes of 3? They're both null or none, right? What did we say the value was when they were both null or none? 0. So we're going to return 0 here. Which one's bigger? 1 plus 0, 1 plus 0. It doesn't really matter, right? It's the same answer. So we just return 1 here. So what you see is that in the end, our final question, right, is which subtree is deeper? The left subtree or the right subtree? And we get 1 plus 3 or 1 plus 1. And what we return is 3, right? So our deepest depth is 3. Right? So what's the time complexity and what's the space complexity of this, right? So the time complexity of this, right, since we have to iterate through each node, right, and each node, we have to go through each node, right, which means we'll go through each node at least once, which means that the time complexity here is going to be linear time, right, where n is the number of nodes. And so the space complexity here, although we're not allocating any memory or anything like that, recursion isn't free, right? So each call we make is going to cost a stack frame. We're making n calls where n is the number of nodes. So we're going to be spending linear space there where n is the number of nodes. And the memory we're using is in terms of stack frames. So that is maximum depth of a binary tree 104.